Digital logic circuits are the fundamental components in computer engineering. We can interpret continuous electrical signals as logic values. We can build circuits that operate on these logic signals. Boolean logic represents the logical operations that these circuits perform. Combinational logic performs Boolean operations on inputs to produce outputs. The output is a combination of the inputs. Combinational logic does not have memory. Sequential logic operates on stored values as well as direct inputs. Registers allow us to store the value computed earlier in the circuit and use it in a later computation. We use both diagrams and text to work with logic circuits. On the left, we have some schematic symbols for logic gates. The top row we have a NAND gate and an AND gate. The circle on the right-hand side of the NAND gate stands for inversion. NAND is the AND of the input signals followed by an inversion. In the middle row, we have a NOR gate and an OR gate. In the bottom row, we have an inverter and an exclusive OR gate. On the right-hand side, we have a statement in a hardware description language. On the right-hand side, we have a description in the Verilog hardware description language. This statement assigns to X the NAND of A and B, not parens A and B. Combinational logic gates operate continuously on their signals. The input signals arrive continuously and the output signal is generated continuously. Here we can see that the output of the NAND gate goes low when both of the inputs are high. When one of them changes, we can connect together logic gates in order to perform more complex functions. In this case, we have a NAND gate and a NOR gate. They share one signal. They compute different functions. The Field Programmable Gate Array, or FPGA, is an important platform for building logic gates. One common type of FPGA uses a memory as a lookup table to implement a truth table in circuitry. Many of these also include a register to store a value. Field Programmable Gate Arrays have a number of these programmable logic cells. They also have programmable circuitry. They also have programmable interconnect to connect together the various gates to create complex logic circuits. We often design logic using hardware description languages. It's also useful to look at a schematic to help us understand the logic. The first assignment in the HDL creates an AND gate that computes the AND of A and B. The second performs an AND on A and C. The third assignment computes the OR of two intermediate signals, X, which comes from the lower AND gate, and O1, which comes from the upper AND gate. We can use simulators to help us analyze and debug our logic circuits. We call the circuit itself that we're designing the unit under test, or UUT. The simulation code that surrounds the unit under test is known as a test bench, as an analog to how we would physically test a circuit. The test bench provides a stimulus to the unit under test and observes the output. Here's a simple example of a test bench in the Verilog hardware description language. It applies a sequence of inputs and prints some results. We can also look at a diagram to see how the logic signals change over time. Implementing logic starts with a hardware description language. We then use logic synthesis to turn that abstract logic description into an efficient logical set of gates. Next, physical design determines how to map those logic gates into silicon. The result in the case of an FPGA is a bit stream that we can load into the field programmable gate array. Physical design includes placement of the logic into logic blocks in the FPGA and routing of the signals that connect the logic. Here, F1 is connected to F2. The two different placements of F2 relative to F1 give different routes for the wire that connects them. Since all the wires for the logic share the same FPGA, the choice to put a wire in one location means you can't put another wire in that same location. Here we have the connection from F1 to F2. We also need to make a connection from F3 to F4. The red wire is one choice of how to connect F3 and F4. However, it creates congestion or too many wires in part of the FPGA. Moving the wire from F1 to F2 clears the congestion and makes room for the F3 to F4 wire. Thanks for watching.